I have a question about, because I took the quiz,
Yes.
and it's probably going to sound like a really dumb question.
Okay.
But how do you incorporate the negative charge to the Lewis dot structure?
That is a very good question. That is not a dumb question.
It's not a dumb
And
question.
and even if it was a dumb question, we'd still answer it because there are probably 50 other people that have that same question, which also means that it's not a dumb question.
Okay.
Okay. So let's say we have this guy. Okay.
Yeah.
So the way that we would incorporate it, this basically means that we're adding 2 additional electrons, right? So if we go through, we figure out how many valence electrons each of these guys have. Sulfur has how many valence electrons?
What, for sulfur?
For sulfur.
Sulfur has 7, right?
Nope, not 7.
6. I'm sorry, 6.
Sulfur has 6.
Uh-huh.
And oxygen has how many?
Same, 6.
6. And we know that there's 4 oxygens, so 4 times 6.
24.
Okay. And then we have 2 additional ones, right?
Yeah, so it'd be 26, right?
Yep. So then we'll add 2 more because these are the electrons that are being added on.
Yeah.
So all together, that'll be 32 that we're working with. 6 plus 24 plus 2. So in this case, we'd have, who's going to be in the middle?
It's going to be sulfur.
Okay. And sulfur has 6 valence electrons.
Yeah.
So I always like to add the extra electrons to the center atom because I know eventually it's going to go somewhere in the center. You know, we're going to use that to kind of get everything done. And so if we did that, and we're obeying the octet rule, each oxygen has 6 electrons around it. So then I could just write it as this. Okay.
Yeah, the lab helped me so much with these things, with these.
Yeah, isn't it amazing? And then it's also amazing that.
Yeah, I went from being like completely lost to pretty good at them.
That's good, right?
Wait, what was you said? This is a quit for the quiz.
Yeah, the practice exam.
Oh, okay. All right, excuse me for a second.
And then the other thing is that you want to put the brackets around it and remind me that we added 2 extra electrons.
Oh, okay.
Okay, so that's that icing on the cake. You want to make sure to include that. And I have a bad habit when I used to get docked all the time for that stuff in camp. So. Okay. So that's good. I'm glad that the lab helps. That's what the labs are kind of supposed to do. They're supposed to help you get a better understanding.
And the other thing for the lab, I'm pretty much done with it. I have it all like written out, like on a like. But you said you wanted to put it in. What should I use? Say just for doing like the structures or whatever. Like, how do we do that on the computer?
Let's see. So you could use Word, you could use Docs because they allow you to draw, right? Although it takes a little more time to sit there and do it that way. Or you could do it and put it in Paint and make it an image, and then you can import those images. Because then it's free draw in Paint.
Okay.
So because I was gonna just kind of like draw it out and then take pictures of it and load it up as a PDF if that was okay.
That'll work. That'll work as well.
Oh, yeah, that's kind of what I was starting to do.
Yeah, you guys we can do old school, if need be, but you got to get it on the computer at some point.
No, yeah, no, for sure. And then because I know I did some for you know, like we're on question 2, you're supposed to use the little things you gave us, the cutouts.
Yeah.
Okay, I numbered them if that's okay. I put them in this all in the same picture, but I numbered them. Is that
Okay,
fine?
that'll be good. Yeah, that'll be fine.
Okay, great.
Long as I'm able to, yeah, you want to make it clear for me because sometimes I get special.
Dr. Henry,
Yes.
can you show me how to do if the element is symmetric or asymmetric? I'm confused in this question.
Yeah, we can actually do that real quick here. Okay, so let's talk about symmetry, right? So symmetry deals a little bit with, well, actually a lot with polarity, right? So if we talk about polarity, I'll give you some examples. So if we have, I won't make you guys do the structures. I'll draw them out for you. So we have carbon dioxide. And I'm actually going to go over this in lecture again. You'll see it twice. Okay. And so in the case of carbon dioxide has, if we looked at it, we want to talk about, first off, bond polarity. Let's see, type it in, bond polarity. Bond polarity is the polarity between two atoms. So it's for that particular bond, right?
Mm-hmm.
Can you repeat that again? You said it's what? I'm sorry.
It's between two atoms. It's the bond
Okay.
between two atoms, bond polarity, because this is a bond between carbon and this oxygen. Okay.
Okay.
So in this case, we're looking at the bond polarity. Now, the way that we determine the bond polarity is based upon what we call electronegativity. I'm going to show you a quick way of determining electronegativity, and I'm going to show you a more in-depth way with numbers and all that stuff of determining the who has more electronegativity, and then rules that are associated with it. The quick way of determining electronegativity is the closer you are to being a noble gas, the more electronegativity you have. Okay, so if we look at our, I'm gonna switch my sharing for a minute to this, and I'm gonna pull up P table. Can you guys see my blue screen? I may be able to pull up P table.
I can see it.
You can see it. Let me pull up P table and then drag it over. Okay, do you guys see P table now? Or did it freeze? Can you guys see P table?
Yes.
Yes.
Good. Okay, so the closer you are to a noble gas, the more electronegative you're going to be. So fluorine is going to be the most electronegative, and electronegativity actually will decrease as you go down, right? So chlorine will be less electronegative than fluorine. Fluorine is going to be the strongest guy. Then if we go from right to left, right? Oxygen is a little less than fluorine. Oxygen is greater than nitrogen. Nitrogen is greater than carbon. Carbon is greater than boron. Okay, so in terms of their desire to get an electron, these guys are going to be stronger than carbon, right? So that means that they're going to have a strong pull for that electron. Okay, so when we're talking about that C double bonded to an O, these guys are sharing electrons. Now, the question is, are they sharing evenly or unevenly? How many of you guys have siblings? An older sibling or a younger sibling?
I have an older sibling.
You have an older sibling? Good.
Just us two, though.
Okay. So, yeah. So you may relate to this a little bit more than others. So as a kid, when I was growing up, my parents, because we were poor, we would get one really good gift. So we'd get a PlayStation or something like that. That would be the equivalent of what we had. We had an Atari, you know? So, but we'd have to share that PlayStation, right? And so the way that I looked at sharing was, since I'm oldest, I get it most of the time. So I would get it about 90% of the time. And my sisters, I have 2 sisters, they would get it about 10% of the time. I didn't care how they get it, but I got it 90% of the time. Okay, you see how that worked?
Yeah.
Okay, so in other words, we're sharing because they get to use it, but we're sharing in favor of me, right?
Okay.
Okay, so that's the way life should work, right? So everything should be revolve around me. Is that not the way it should work? You guys are not agreeing with me here. I'm a little worried. Okay, so that's what's going to happen in the
I'm a
case.
bit lost, to be honest.
You're a bit lost. What do you mean? Do you share with your siblings?
Yes.
Okay, so and you're a younger sibling, right?
Yeah, the youngest one.
Yeah. So if you're the youngest sibling, doesn't your older brother or your older sister, like if you guys have to share, don't they take the toy more than you did?
They do.
They do.
They do, right? And according to the rule is, my mom says share. I'm sharing, right? If I get 90% of the time, we're sharing because they get it 10% of the time, right? Isn't that sharing?
Yes.
Loosely, by definition, it's sharing. It's sharing unevenly, right? I get it 90% of the time. They get it 10% of the time.
It's
Okay?
uneven.
It's uneven, right? So when we talk about the electrons
So you're saying that to make it 50 and 50, half and half?
No. I'm not saying we're making it 50-50 because that's not reality, right?
Right.
So the only time that it's going to be reality, that it's going to be 50-50, is if both parties are like equal, right? Or
Right.
they have the same amount of electronegativity. But in reality, that's not the case. We know that fluorine is much greater than hydrogen, right? Fluorine is much stronger than hydrogen. So fluorine is going to get the electron the majority of the time.
Right.
Okay. So does that make sense?
That makes sense now.
Okay. So in this case, oxygen is more electronegative than carbon. So the electron, the arrow points to which way the electron is going to be spending the most time with. Okay. So the electron is going to be spending more time with oxygen than it is going to be spending with carbon. Okay. So the electrons that are shared here, they're really going to be spending more time over here than they are going to be spending with carbon. Now they're being shared, right? But oxygen is getting it the majority of the time. Okay. Now, on the other end, we have another oxygen, right? So the bonds here, right, are electrons that are being shared. So these electrons are spending more time with that oxygen, right, that are being shared. Okay, so since the electrons are spending more time with that oxygen over here, and the electrons are spending more time with that the other oxygen, right, we want to look at what we call molecular polarity. Right? We already know that bond polarity, this guy is favored. Oxygen is favored in terms of bond polarity. So molecular polarity is looking at the whole molecule, right? So we have to look at the thing together. Now, if you guys, let's say we had twins, right? And you were sitting in a wheelie chair, right? Chair with wheels on it, and you had a twin on each side. Now, these twins are exactly the same. They have the exact same strength. They look the same. They're the same height. They have no advantages over each other, right? If they were grabbing you both by one hand and the other hand, then who would win?
No one.
No one.
No one would win, right?
No,
And so that's what's happening here. You have twins on both sides. You have oxygen on both sides. Both of them are pretty strong compared to the person in the middle. But since they're exactly the same on both sides in terms of polarity, it's not going to have a polarity as a molecule. So bond polarity, oxygen is going to be favored, right?
Can you see me, Dr. Henry?
What was that?
Can you see me? Because I turned on my video camera.
I see you.
Yeah, I can see you. Yes.
Well, is this like the game that you're telling me who would win if they would do this to you? Like,
Yes,
who would do
exactly.
this?
Exactly. Yes. Yeah. And so bond polarity, they're going to be exactly the same. But molecular bond polarity, oxygen is going to win. If we look at just that one bond, oxygen is going to win. But molecularly, nobody's going to win, right? So neither oxygen is going to be greater than the other. Okay. So in that case, it would be considered to be nonpolar, meaning that it doesn't form a pole. Okay. So now,
I never understood the difference between polar and non-polar. Can you tell me like the difference of it, please?
yeah, so that's what we're talking about right now. So
Right.
when we talk about polar, so this is the molecular polarity.
Right.
Bond polarity. Bond polarity is looking just between the bonds. Polarity just basically means that one of the atoms is stronger than the other. When we're talking about a molecular polarity, we're looking at the whole molecule. So you're saying that the molecule is being shifted to one of the atoms more so than the other atoms when we're talking about the whole molecule. Does that make sense?
Makes sense.
Okay. So if we looked at just carbon and oxygen, so carbon and oxygen form a triple bond. So the electron is going to be spending more time with who? If we know that oxygen is more electronegative.
The oxygen?
Oxygen.
The oxygen. So the electron is going to go where the arrow is going. So that means that they're spending more times around the oxygen than the carbon. So the bond polarity in this case is towards
Oxygen.
the oxygen. So the way that we can depict that, we would say this guy is partially, so this delta, this is delta, lowercase delta. Oops, sorry, messing up here. This guy is partially negative because electrons are negatively charged. So that means that the electrons are spending more time on the oxygen than they're spending on the carbon. And this guy would be partially positive because if you're not negative, you have to be positive, right?
Mm-hmm.
Okay, so does that make sense?
Uh-huh.
Okay,
So does the bond refers to the electronegativity, right?
so the bond polarity refers to the electronegativity, yes. Okay,
Okay.
now molecular polarity is summing up everything, right? So in this case, this guy is the molecular polarity because we're looking at both bond polarities and they're going to kind of cancel each other out because they're both equal in strength. Okay, does that make sense?
Yeah.
Yes.
Okay, so now I'm going to add a layer onto it because the question was about symmetry, right?
Yes.
So symmetry basically means that you kind of have equal pull on both sides, right? That it's the same, like on both sides. Asymmetry or asymmetrical basically means that one side is favored over the other. So in this case, where we're talking about carbon triple bonded to oxygen, is one side favored over the other?
Are you referring to out of the two oxygens or just
No,
oxygen
I'm talking about here, this one right here, this one right here,
Okay.
right there. So is one side favored over the other?
No.
No?
Yes, it is.
Yes.
Because one's losing and one's gaining,
Well,
right?
it's not necessarily one is losing, one is they're still sharing, right? Remember,
Yeah.
it's still being shared. It just means that the electron is spending, so these electrons between them are spending more time around the oxygen
Oxygen
than they're spending around the carbon.
Then the carbon.
Okay, so you're right, it's uneven, right?
Yeah.
So since it's uneven, then that means that it's asymmetrical, right? It doesn't have symmetry.
So uneven.
Okay,
So it's like you said earlier about the comparison between you and your siblings.
yes, since I'm bigger at the time, I say at the time I was bigger, right? So then I could bully my sisters to sit there and say, you know what, you're only going to get to play with it for 10 minutes and I get to play with it for an hour, right? Fair?
Right. Yeah.
So I actually have another question because it was about the quiz before we start lecture, but maybe that's what we're probably going to go over. I
Yes.
forgot what the IUP what is it that IUPAC is? It has to do with
IUPAC.
IUPAC, yeah.
We'll talk about IUPAC here in a second.
Okay.
So, actually, we have kind of talked about it, but you guys may have not picked it up. IUPAC is just basically means of nomenclature, right? And
Yeah.
so, actually, we haven't talked about that particular question. That question won't be in your.
All right. So just hold on then, because
Just hold on. Hold
Okay.
on. Yes.
Thank you.
Hold on. I was being ambitious. Okay. So this guy, in terms of symmetry, right? So we know that this guy is asymmetrical. So okay. Now, what about here? If we split it down the middle, would it be symmetrical? Or would it be asymmetrical?
It would be symmetrical.
It would be symmetrical. So in this case, this nonpolar molecule is symmetrical. Okay, so now I'm going to ask you another question. And I want you guys to think about this. So if we have this molecule, I'm trying to make room, find room to write more stuff. So if we have HCN, let's see, I think that's it. 1, 2, 3. Actually, let's do this. Okay, so if we have this molecule here, right? Do you guys see it up top, the HCN?
Yeah.
Yeah.
Hydrogen has the weakest electronegativity. Carbon and hydrogen are really close to each other. They're like really, really close in terms of electronegativity. So when we look at those guys are about even to each other, okay? Almost even. But nitrogen is much stronger than carbon, okay? So which atom is going to be favored in terms of carbon or nitrogen?
Nitrogen.
Nitrogen.
Okay. So nitrogen is going to be favored because nitrogen is more electronegative.
Yeah.
I was about to ask you why nitrogen can be the most favored, but now you just said it, so I just understood right now.
Okay, good.
Okay.
So, and we know that hydrogen is a little bit less than carbon, just a little bit. So we would draw like a little arrow if we're going to draw an arrow. But in most cases, because they're so close together, they're almost exactly, be a little tiny arrow. Okay, so if we looked at this, right, and then we said, okay, so what is the molecular polarity? Okay, so we're looking at the whole molecule as a whole. So who's going to be favored as a molecule? I'm going to draw that one in.
Nitrogen.
Nitrogen.
Overall, nitrogen is going to be favored. Okay, so the blue represents the molecular polarity, right? So if one of the sides are favored, is that going to be symmetrical or asymmetrical?
It'd be asymmetrical.
That's going to be asymmetrical. Does that make sense?
Yeah. Makes perfect sense.
Symmetrical. Oh.
Dr. Henry, today we're going over nomenclature. That's not going to be on the exam, right?
No, we're not going over nomenclature. We're going to finish up about polarity, actually. That's where we left off at. So we're going to finish up polarity, and then that's all you guys have to worry about for your exams, right? And then so when you guys get back, we'll hit nomenclature running.
Okay.
We'll have a lot of nomenclature. But actually, we'll talk about nomenclature and also geometry. So you guys won't have any geometry in this exam.
Okay.
Even though it was in your lab.
This is taking us back to high school math, I bet. About geometry.
Dr. Henry, we on the exam, oh my gosh, we do have the molecular geometries on there, or on the
I know on your practice exam you guys do, but on your actual exam you guys
so it's okay, so it's just you're just kind of giving us like a little warm up of what to expect when we come back.
Yeah, exactly. I'm just
Okay,
prepping you. I want you to be over prepared rather than under prepared, you know?
Okay.
Okay.
Thank you.
Okay. Good. So are you guys with me so far? You're good? So does that help?
Yes,
Yeah.
it does. Thank you.
Okay. So those are all good questions. So let's actually get to the lecture, and then we'll answer some more of those questions. And then at the end, if there are other questions, we'll go into my office hours and handle that if we're running. Okay? Because I know that I have a few people that need to be that are special.
I'll be there.
Okay, so let me find my lecture notes. It's gonna ask, so what class is this again?
CHEM-002A.
CHEM-22.
CHEM-22? Okay.
Yes.
Okay. CHEM-22 or CHEM-2A? Okay, got it.
Biology.
It's CHEM-2A.
Okay, so we have about, can you guys see my slides?
Yes.
Yeah.
Yeah.
Okay, so we have been
Yes.
talking about Lewis dot structures and how to do Lewis dot structures. I'm gonna put the last one that we drew. Actually, I'll put a different one. Let's do water. So the Lewis dot structure for water would be what? Who's gonna be in the middle?
It would be oxygen.
Okay. And how many valence electrons does oxygen have?
6.
I'm gonna cheat a little bit. Can you guys see my little blue, or is that too light?
No, we can see it.
I can.
Okay, and how many valence electrons does hydrogen have?
1.
Okay, so we know that's gonna look something like this.
Yeah.
Okay, so we know that this guy, if we count the number of electrons around oxygen, it obeys the octet rule, meaning that it has 8 electrons around it. We know that hydrogen is an exception because it only wants to be like helium. It only wants to have 2 electrons around. And we have 2 electrons around helium because we know that this bond represents the sharing of 2 electrons, right?
Yeah.
Okay. So we have a total of 8 electrons around oxygen. 2, 4, 6, 8. You guys agree with me?
Yes.
Okay. So this guy obeys what we call the octet rule. So when we make reference to the octet rule, we want to make sure that it's obeying the octet rule. Okay. Does that make sense?
Yes.
Okay. Now, there are going to be exceptions, and I will talk to you about those exceptions specifically, and I'll show you those exceptions. Okay. Now, the other thing I wanted to talk to you about is what we call lone pairs. Lone pairs are the electrons that are not going to be involved in bonding. So in this case, the ones that are these electrons up here and these electrons up down here are the ones that are not involved in bonding because they're not being shared between the hydrogen and the oxygen. Okay. So does that make sense?
Yes.
So when I ask you how many lone pair does this guy have?
2.
2.
It has 2 lone pair.
Mhm.
1, 2. If I asked you how many lone pair electrons this guy has,
It has 4.
it has 4. So do you guys see the distinction between the two?
Yeah.
Right.
Okay. So I'm going to teach you something because I know you guys have been doing it with your homeworks, right? So there's a term called formal charge. So the formal charge is valence electrons on the atom minus the lone pair electrons minus the number of bonds. Okay. So valence electrons. Okay. So if we're talking about each atom has to be calculated independently. So in this case, we have technically 3 atoms that we're looking at. We're looking at an H, we're looking at an H, and we're looking at an O. So if we're going to calculate the formal charges of the H, the hydrogen, so then how many valence electrons does hydrogen have?
1.
It has 1 valence electron minus the number of lone pair. Are there any lone pairs electrons around hydrogen?
No.
There's 1.
Lone pair.
Oh, no. There's not.
0.
Sorry. I'm so sorry. No.
Okay, there's 0.
Yeah.
And then how many bonds do we have?
1.
1.
What
Okay.
were you referring to, the bond, Dr. Henry?
The bond represents the line between the hydrogen and the oxygen.
Oh, okay.
Remember, bond, right? Because that's what it is, it's bond.
Right.
Okay. Okay, so if we do this other hydrogen, it's going to be the same thing, right? Because we have 1 valence electron minus, there's no lone pair, minus the number of bonds. There's 1 bond.
Oh
Okay.
my God.
So in this case, we have oxygen that's in the middle, right? So then how many valence electrons do we have? How many valence electrons does oxygen have?
4. Well, it has 6 in total, but it has 4 around it, right?
No, we're not. We're saying valence electrons. We're
Oh,
just
okay. Sorry.
valence electrons.
So
So we
6.
have 6 valence electrons.
Mm-hmm.
Okay. How many lone pair electrons?
Okay. 4.
Okay. So that's why it's important that you guys understand the definition, right?
Yeah.
Okay. And then how many bonds does it have?
2.
That's 2.
So if we add this up, that should equal 0.
0.
Okay. Now, the thing about formal charges, the goal is when you're trying to get things set up on terms of formal charges compared to the Octet rule, there is a distinction, right? There can be a distinction. In this case, this just happens to work out. The Octet rule and the formal charge rule are the same one. So the goal for the formal charges is to have a formal charge of 0 or as close as you can get to 0. You guys get that?
Yeah.
Okay. So goal is to have a formal charge of 0 or as close to 0 you can get. Okay, so formal charges just kind of helps us understand whether that molecule is going to be stable and how stable it really is going to be. Okay, and so sometimes we have structures where we can have multiple structures that we can make, but by doing the formal charge, it'll let us know which structure is more correct. Does that make sense? And I teach you it because some of you guys are going to take this class and go to the next level. Okay. So Erin, are you there? She asked, are we counting pairs or are we just counting lone electrons? So in the case, we're counting lone electrons. So that's what I call lone pair electrons. So it's the electrons that are just in those lone pairs, all the electrons in the lone pairs. Okay. Does that make sense, Erin?
Yeah.
Okay. Okay. So are you guys with me so far? Do you want me to give you one that's kind of hard?
Yeah,
Doesn't work out to be
please.
0?
Give us a juicy hard one.
Okay. I'll give you a juicy hard one. Okay. Oops. Let me get my eraser. Okay. A harder one. Okay. So we know that we did C. Oh, so carbon monoxide looks like this. So if we wanted to calculate the formal charge for carbon monoxide, so we have formal charge. Okay, so for carbon, how many lone pair do we have? How many valence electrons do we have? Getting ahead of myself.
4.
4.
Carbon has 4.
Carbon has 4 valence electrons. Minus,
Mm-hmm.
how many lone pair electrons do we have?
1.
2.
Oh, lone
Oh,
pair
1, 1.
electrons.
1.
Lone pair electrons.
Oh,
Have
2.
three.
You're right.
So we have 2, right? 1, 2.
Right.
yeah.
Okay. And then how many bonds do we have?
3.
Okay. So we add this up. This guy gives us -1. Okay.
Mhm.
Oxygen.
Mm-hmm.
Okay. How many valence electrons does that guy have?
6.
6.
How many lone pair electrons does it have?
2.
2.
And then how many bonds does it have?
3.
3.
So then that's going to be a +1. Okay. So now this guy is an example of, we can, regardless of what we do, we can't get it to be any other structure than what it is right there. We can play with it as much as we want to. We're going to end up with the same structure if we're going to obey the octet rule. If we were going to obey the formal charges rule, we could get something that's kind of weird, but we know that that doesn't really exist either. No, actually, we couldn't get anything that's weird either. So it would just screw up the whole octet rule. So we know that this is the best that we can do with these circumstances, because we know that this is what the structure looks like. So, but you notice this guy is a -1 and a +1, right? Normally, under the best circumstances, you want your negative value on the one that is the most electronegative. So we would normally want it on oxygen. And then we'd want the positive on carbon, because carbon is less electronegative. However, this guy is an exception. It's also, we know that carbon monoxide, you guys know carbon monoxide is a poison.
Yeah.
One of the reasons why it's so poisonous is because it's still kind of reactive. It likes to react because it doesn't have a lot of stability. The fact that this isn't really close to 0 kind of helps us understand that it's not as stable as it would like to be. So it's still going to try to react to try to get some more stability associated with it.
So having the background knowledge that you just provided us, we would know that. But say it was like a different scenario, how would we be able to check? Would we just assume that if it looked like this and it wasn't in reverse, then it would be wrong?
No, you wouldn't assume that it was wrong, right? And so that's the kind of thing that you're still kind of learning, right? So
Okay.
under the circumstances that you guys are at, this is one of the reasons why I have you guys do formal charges in your homework, but on the exam, I don't worry so much about it, because formal charges is a little more complicated. You need a little more stuff under your belt. And if you guys were in my 1A class, you guys are responsible for it. But for my 2A class, this class, which is the intro, you guys aren't. But I like to teach it to you so you guys can do it. In most cases, if I ask you anything about a formal charge, they'll be just calculate the formal charge, not to decide whether or not that structure is right or wrong.
Okay.
Because you guys are going to be reliant on the octet rule. Okay. Except for the exceptions that I gave you. Okay. Okay. Does that make sense?
Yeah, I was just concerned. Yeah, like you explained about the checking and balancing part, but that's in a later.
Yeah. Okay.
course.
So are you guys all with me so far?
Yeah.
Okay. And then, so the exceptions are going to start making more sense to you when you use the formal charges. And you're like, oh, okay, I get it. Because they use the formal charge to allow that exception. Okay. So, and I promise you, it'll start making a little sense. I know it's all black box right now. So we've already talked about polarity, right? So polarity basically means that something is going to have poles. It's going to have a positive pole and a negative pole. So when we were talking about carbon monoxide, I said that this guy is partially, put my dots here. This guy is partially positive, and this guy is partially negative, right? Now, I said partially. What do I mean by partially?
Almost, but not quite.
I like that. Almost, but not quite. So if we think about things in terms of wholes or halves, right? Or wholes or parts, right? Partially means it's part, right? If we think about something being whole, wholly positive or wholly negative, then we'd be talking about ionic compounds. So these guys are not fully positive or negative because they are sharing the electrons. Electrons are being shared between the two of them, right? And so one guy is going to get it a percentage of it, not the whole time. Does that make sense? Where like if we were talking about sodium chloride, well, we know that sodium is positive and we know that chloride is negative. But when they come together, we have both that positive and that negative. But if they're separated, we know that sodium is going to get that, it's going to be positive, and then chlorine is going to get the electron and it's going to be negative. Does that make sense?
Yes.
Yes.
Where these guys are still sharing the electron. Okay, so we use the term pole. So we have a negative pole and we have a positive pole. This guy is my positive pole. This guy is my negative pole. Okay, and so you'll also see the term dipole, right? Di meaning two, pole, two poles, a positive and a negative. Okay, so you'll see the term specifically dipole moment. That basically means that you're looking to see when the electron is going towards that, right? So it's when your electron is moving towards the other guy, right? Where it's spinning the majority of the time. That's considered your dipole moment. Okay. Don't worry, I'll give you more examples. So don't freak out yet. Okay, so we have things that are, let me clear. We have things that are nonpolar. Nonpolar basically means that they're sharing evenly. So if something is shared evenly between two atoms, it's considered to be nonpolar. Or if we looked at the polarity of the molecule, right, it's being shared evenly between the outer sides, it's considered to be nonpolar. Okay, does that make sense?
Yes.
Yes.
So if we did something, we'll do in the case of hydrogen sharing with hydrogen, right? These guys are twins. So they're the same strength. They're going to be exactly the same. So no one is going to be favored. So in this case, we know that hydrogen gas is nonpolar. Does that make sense?
Makes sense.
What about
Yes.
oxygen gas? Oxygen and oxygen.
It would still be nonpolar.
Right.
It's still nonpolar. That is correct. Okay. And then I gave you the other example where we had carbon dioxide. This guy is also considered to be nonpolar as a whole, right?
Yes.
As a molecule. So polarity,
Why
we can talk about bond polarity, or we could talk about molecular polarity. Okay? Bond polarity, if we just looked at the bonds individually, it would be polar, right? Because oxygen is favored this way, and then the oxygen is favored that way, if we're looking at just the bond. But if we're looking at the molecule, we're looking at the whole thing together. Does that make sense?
Okay.
Okay. So we want to make sure that we're asking when we're talking about polarity, is it bond polarity or is it molecular polarity? If there's only two things, it's easy because it's only two things, right? You're looking at bond polarity. That defines
Dr. Henry?
What was that?
Dr. Henry, I think, I don't know if it was Alan or somebody asked, like, why, when you had the 3?
Yeah.
And maybe he needs another visual.
Yeah.
He wanted to know why, like,
Why is
so if you
it
split it down the
nonpolar?
middle, yeah.
So if we just looked at this one bond, so this is our molecule, but we're only going to focus on one side at first, right? If we look at just this side here, we'll call this side A. We look at side A. So we're looking at the bond between carbon and oxygen. Okay, so who's going to be favored?
It's going to be the oxygen.
Oxygen.
Oxygen is going to be favored, right?
Mhm.
So if we did the partial, so that means that this guy would be partially negative, and this guy would be partially positive, right? Okay, so if we look at side B, who's going to be favored?
Oxygen.
oxygen again. So again, this guy is going to be partially negative, and this side is going to be partially positive, right? Okay, now since they're going, remember, Alan, remember, they're twins on both sides of you. Is either of those twins going to pull you harder than the other?
No.
No, right? So then in that case, are you favoring one of those twins?
No.
No, you're not, right? So then that means that it's non-polar. Nobody's being favored
They're equally.
overall. They're equal. Yeah, exactly. Okay, so if we look at water, can you guys see my water molecule?
Yes.
Right? So if we talk about water, what is the polarity for hydrogen and oxygen? The bond
Polar.
polarity. It's polar. Who's going to be favored?
Your
Oxygen?
oxygen.
Oxygen is going to be favored. Okay, and then that's the same thing that's going to happen here. So if we look at molecular polarity, is anybody going to be favored?
No, nonpolar.
No.
Are you sure?
No, it's oxygen's gonna be favored, right?
Yeah, because both of them are going towards oxygen, right?
Yeah.
In this case, you know, the guys on the outside, right? They were pulling evenly on the outside. So you're kind of stuck in the middle.
Mhm.
In this situation, you're the one that's pulling those guys because you're much stronger than they are. So you're going to pull them towards you, right?
Yeah.
So in this case, it's going towards the oxygen overall.
Oh, I follow you.
Okay, does that make sense?
Yeah.
What was that again, Dr. Andrea? The signal kind of went off with me.
I said in the case of water, because the person that's the strongest is the person in the middle, right? So in this case, it's like you're pulling both of those people who are really weak towards you.
Right.
Okay. So then your favor, you know?
So that would be polar then.
Yeah, so this guy would be a polar molecule. And each of the bonds are also going to be polar. So polar, and each bond will be polar.
Wait, so that means oxygen is being more favored since hydrogen has less electrons than
That's right. That is correct.
oxygen. Oh, I get it now.
Okay.
Like playing tug of war again, two against
Yeah.
one.
Yeah, exactly. It is. That's exactly what it's like.
Now you can move on now.
Okay. Thank you. Okay.
De
So, okay. So when we talk about nonpolar covalent bonding, that basically means that things are being shared evenly, right? And so this is kind of showing you, the bubble shows you it's being shared evenly, right? So both of these are the same size. They're sharing it evenly. Now, polar basically means that you're sharing unevenly. So in this case, this is showing you that Y gets the electron more times than the X does. So that's uneven sharing, okay? And then this is an example of ionic bonding, where the electrons are being transferred from the M to the Y. And so then X is, I'm sorry, not Y, M to the X. X is negatively charged and M is positively charged because you're having a transfer of an electron. So does that make sense?
Yeah.
So we could have two types of covalent bonding, non-polar covalent bonding, or we could have polar covalent bonding. What it means to us is non-polar is evenly shared. So that means you're getting it 50% of the time. Everybody's getting half, right? In that case, everybody's happy, 50-50, okay? Or we could have polar covalent bonding, 10%, 90%, right? Uneven. Make sense? Okay. So electronegativity. So electronegativity, again, is just the ability to attract those electrons, have the electron being pulled towards somebody more so than anything else, right? And so if you take a look here, there's a general trend. So as we go from left to right, the electronegativity is going to increase. As we go from as we go from bottom to top, the electronegativity is going to increase. Or if we could say, it decreases as it goes down, right? So fluorine is going to be the most electronegative. And then francium is going to be the least electronegative. Okay, make sense?
Yeah.
Okay, now you'll notice there are going to be some crazy exceptions in here, right? And that's what you'll see. Now, the way that you determine numerically how we determine who is going to be more electronegative and what type of bond we have, is it a polar, if it's a polar bond, a nonpolar bond, or a quote ionic character bond, right? Is by looking and taking the difference of the electronegativity, right? So for instance, there is a range, and I'll write out the range for you guys. So if we go from 0 to, sorry, do this the right way. So if for value is less than, can you guys see that? For value is less than or equal to less than or equal to 0.4, this guy is going to be nonpolar. If it's greater than, if it's type, if it's greater than 0.4, but less than 1.8, then it's going to be polar. And then if it's greater than 0.8, or equal to 1.8, then it's going to be ionic or have ionic character. Okay, so now let me kind of explain this to you. Okay, so if our difference is, the difference between the two molecules we're looking at are, if it's less than or equal to 0.4, it's going to be nonpolar. If it's greater than 0.4, but less than 1.8, it's going to be polar. And if it's greater than 1.8, it's going to be ionic, okay, or have ionic character. Okay, so what we would do is we take the numbers. Let's say we're looking at fluorine, a bond between fluorine and oxygen. So you take the one who has the higher value. Fluorine has a 4.0 value. We subtract the value of oxygen. (3.4). And what do we get?
0.4.
You mean 0.6? 4 minus 3.4? Is that 0.6?
Oh, yeah.
Okay, so in that case, right, where does that lie? Is that going to be polar? Is that going to be nonpolar? Or is it going to have ionic character?
It's going to be polar.
It's going to be polar. So we know that it's polar, and it's going to be favoring fluorine because fluorine is greater than oxygen. Does that make sense?
Yes.
Okay, so let's look at carbon and hydrogen. Okay, carbon, where's carbon on here? Can you guys see my table?
Yeah, it's 26, 2.6 purple.
So it's 2.6. And then hydrogen,
Hydrogen is
2.2.
2.2 green.
okay. So 2.6 minus 2.2.
0.4.
Okay, is that going to be polar or non-polar?
0.4 is nonpolar.
Okay, does that make sense?
Yes.
Okay, do you want to do one more?
Yes.
So that
Yeah.
That's a hard one.
Give you a hard one?
so that key up there, that is just an indicator of whether or not it's nonpolar, polar, or ionic with an ionic character.
That's right.
Okay.
So let's do, oh, this is a good one here. Let's do,
Can you show an Ionic example, Dr. Henry?
yeah, I can't show an ionic example, but let's do the carbon and the sulfur
Okay, thank you.
first. So carbon and sulfur,
Carbon is 2.6.
2.6.
Sulfur is 2.6. 0.
Okay, what would that be?
Ion. No.
Non-polar?
Yeah.
Non-polar, because it's less than or equal to 0.4, right? 0 is less than 0.4. Is that right?
Yeah.
Okay. So
Yes.
let's do chlorine and lithium.
3.2. Lithium is 1.0 equals 2.2.
So would that be?
Greater than, so ionic.
Ionic?
Ionic, right?
Yep. Piece of cake?
Yeah.
Yep.
Okay. Okay,
you.
that's it. And also, the other thing is that we know that metals and nonmetals, when they come together, in most cases, except for one case, are going to form what we call ionic bonds, right? So we know that that's definitely helps us in that regard. But this is just to kind of give you some guidelines. Does that make sense?
Yeah.
Okay, good. Oops, got carried away. So this is just showing you what we just did, right? Okay, so we know that if we're sharing 2 electrons, that's going to be a single bond. If we're sharing 4 electrons, that's going to be a double bond. If we're sharing 6 electrons, that's going to be a triple bond. Okay, and that's the most you're going to get is a triple bond. Okay. Technically, carbon could form a quadruple bond, but it's unstable and you don't get the right bending, so it never happens. Okay. Does that make sense?
Yeah.
Okay.
As a joke, and would there be a quad bond since quad
Nope.
means 4?
Yes. Yes. Not quadruple. Yeah.
Yeah, but there's no such thing as that. Sorry.
Yeah. Okay. So we've already talked about the center atom. You guys have already done that. You guys are already ahead of the game because you already know how to draw your little structures, right? Okay, so now let's talk about exceptions to the octet rule, right? And we all know that the guy who has the, except for in the case of things that are being paired with oxygen, I mean, things that are being paired with hydrogen, hydrogen will never be a center bond, right? We all know that.
Yep.
Hydrogen will never be in the middle ever, right? If we're having to make a choice who's going to be in the middle, right? Long as it's not hydrogen, hydrogen will never be in the middle. We know that carbon likes to be in the middle, right?
Yeah.
Because it's less electronegative.
And it's a
So we
whole.
want to use, yes, and it's a whore, yeah. Okay. So there are exceptions. Okay, you guys are going to hate me, but there are exceptions, right? So one of the exceptions is if we have an odd number of electrons, of valence electrons. So the total valence electrons are odd, right? It's going to be an exception, like nitrogen monoxide. This is nitrogen has how many valence electrons?
Has 2, 4, 5,
It has 5 valence electrons, and oxygen has how many?
6,
Okay, 5 plus 6 is what?
11.
11.
11. So in the case of nitrogen monoxide, you're going to try to get the one who's the most electronegative to reach its octet, and the other guy is going to be short. Okay, so the only way that that's going to work is if we have a double bond between the nitrogen and the oxygen. So that means that oxygen has 2, 4, 6, 8 around it. Then nitrogen will only have 7 around it. 2, 4, 6, 7. Does that make sense? Okay. There's no way.
In
What
that
was that?
example, what's the original structure then? For
That is the original structure. That's it. That's all you're going to get, right? Because you can never reach an octet. It's an odd number of electrons.
right.
Are you going to
Never
give us
happened.
something like that on the exam?
Oh yeah, I definitely will give you something like that on the exam.
Wait, for the one that's due tomorrow or the
Yeah,
Oh, okay.
because I'm making a point to stress this is going to be on the exam, right?
Oh, okay.
And it was in your lab, and it was actually in one of the practice questions.
How many other exceptions are you putting in?
All the exceptions, you should be familiar with all of them because they're real easy. Odd number, right? If it's an odd number, you can never reach your octet.
Yeah.
So, I always make the bet with students. I always earn a little extra cash on the side by making this bet. Show me a way that you can reach your octet with an odd number of electrons. So I give them something that I know that it will never work. So I make sure I win, right? Okay. So, and if you guys remember, you guys actually did the same thing because you had NO2, right? So you've had examples of this already. So there's no way that you're going to be able to reach your octet in that case, right? So again, you want to make sure that the oxygen will reach its octet. We look around this oxygen, 2, 4, 6, 8, around the oxygen, and then this oxygen, 2, 4, 6, 8, it reaches its octet, and then nitrogen will be 2, 4, 6, 7, right? So it'll never reach it because there's an odd number of total valence electrons. Does that make sense? Okay. So that's one exception. Our second exception is when we have more than 4 pairs around us. This guy is called hypervalent. And this guy actually happens quite a bit. I'm going to show you something. So hypervalence basically means that you have more than 8 around you. So if we count how many is around this phosphorus, how many do you have around the phosphorus? How many electrons?
10.
2, 4, 6, 8, 10, right? What about the sulfur?
Yeah, 12.
12.
2, 4, 6, 8, 10, 12. Okay. So hypervalence will actually happen because, come on, let me get my key table. I'm like, how are we doing on time? Doing pretty good, huh?
Good. Yeah.
Jamming.
Okay. So these guys that are in the third period and below, all of these guys down here, all of these guys here, all of these guys can be hypervalent. Okay. The reason why they can be hypervalent is because we now have the d orbital to kind of use, because this is the 3D, right? So if it needs to put something in it, there's spaces for it to put stuff in it. So it's able to stick those electrons in that d orbital when it's sharing electrons with another element. Does that make sense? Where
Yes.
all of these guys above it, right? They don't have a d orbital to do that with. These guys here, all of these guys up here, these guys don't have a d orbital. I should include. So they're limited. They can't do that. So they'll never be hypervalent. only the ones that are in the third period and below. Okay, does that make sense? Yes, no, maybe?
Thumbs up, yes.
Okay. Okay, and so the ones that you're going to be concerned about primarily are going to be, you're going to see phosphorus do it occasionally, you're going to see these guys, and iodine is known to do it very well too. Okay. So, but technically all of the guys over here can do it. Okay. See, can you guys see my screen? See the slides?
Yes.
Okay, so that's an example of hypervalence, right? And then I'm going to show you formal charges. So if we do the formal charges, we're only going to do it on the center atom. Actually, we'll do it on both. It'll make it easy. Okay, so if we do the formal charges on the guy that's hypovalent, I mean the odd number, right? Formal charges here. So the N. So how do we calculate formal charges again?
Valence.
Okay, so how many valent electrons does nitrogen have?
5.
Okay, minus the number of lone pair electrons. How many lone pairs do we have around this one?
3.
3. And then minus the bonds.
2.
2.
And that equals 0, right? And what about oxygen?
Oxygen has 6.
Okay, 6 valence electrons. The
Minus-
number of lone pair electrons
4.
and the number of bonds.
2.
Okay, and that equals 0. Isn't that a formal charge perfect? Both of them are 0.
Yes.
Yes.
Okay, so that's one of the reasons why these guys kind of work out. They're more stable in that sense. Okay, so let's do phosphorus here. And then we'll do one of the fluorines because all the rest of them are going to be exactly the same. So how many lone pair how many valence electrons does phosphorus have?
5.
How many lone pair does it have on it?
It has 10, right?
Lone pair electrons.
None.
None.
It has none. And then how many bonds?
5.
It has 5. So 5 minus 5,
0.
okay. And then what about the fluorine? How many lone pair how many valence electrons?
7.
How many lone pair electrons?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14.
You're looking at a single atom, not all of them, just one.
He's 6.
30.
Okay, 6. So there'll be 6. Okay, and then how many bonds?
1.
1.
So 7 minus 6 minus 1.
0.
That'd be 0.
Okay, so again, its formal charge is 0. It's perfect. So that's why it likes it. Okay,
Mhm.
and then what about the sulfur here? Number of
Sulfur.
valence electrons?
6.
7. 6, sorry.
6.
Mm-hmm.
Any lone pair around it?
No.
No lone pair. And then how many bonds?
6.
6 minus 6.
0.
0.
And then one of the fluorine.
Mm-hmm.
Number of valence electrons.
7.
Number of lone pair.
6.
Number of bonds.
1.
Okay, piece of cake.
Yes.
Okay. Okay, so we've talked about odd number or odd number of valence electrons. We've talked about hypervalency. And then we also have what we call hypovalency or deficient. This often will be called deficient valency. Hypovalent or deficient. Okay. So beryllium is a metal that thinks it's a non-metal. Okay. So it likes to form covalent bonds, but it only likes to have 4 around it, 4 electrons around it. Okay. So, and particularly when beryllium is with fluorine, it wants to make fluorine happy because fluorine is strong, right? And so beryllium will covalently link with fluorine, and it will have just 2 bonds around it. Does that make sense?
Mm-hmm.
Okay. So if we did we do the formal charges for beryllium. Beryllium has how many valence electrons?
2.
Any lone pair around it?
No.
And how many bonds?
2.
And then that fluorine, if we look at just one of them, because the other one is exactly the same.
7.
Lone pair,
6.
bonds,
1.
okay. And last one is boron. Boron only likes to have 6 electrons around it total, right? It will also, boron is a metalloid, but it wants to bond covalently with non-metals, okay? But it only wants 6 around it. It does not want to have 8 around it. So it's also going to be deficient. Okay, and if we did the same thing, we'd get the same value. So boron would be 0 because we have, what is it? 3 valence electrons minus no lone pair minus 3 bonds. Okay. Questions, concerns, credit. Okay. And there is occasions that oxygens, certain molecules that have oxygen in them, they're going to not behave the way they're supposed to as well too. But it's rare, okay? Very rare. And I don't think I have any examples of that for you guys. Okay, so are you guys with me so far?
Yeah.
Okay. So the last type of bond. So far we've talked about ionic bonds, we talked about covalent bonds, and now we're going to talk about metallic bonds. So metallic bonds are when metals come together, metals that are going to be interacting together, right? And they're just metals, right? Metallic bonds. Does that make sense?
Yes.
Okay. So now the way that this works is that the metal will actually delocalize its own electrons. So let's say we're talking about sodium, right? So sodium has how many valence electrons?
1.
It has 1 valence electron. So if we do the Lewis dot structure of sodium, we draw it like that. So what sodium metal does, sodium metal will actually sit there and say, okay, I am sodium plus, right? And then it kind of kicks its electron out by itself. And so the electron will be sitting right next to sodium, right? And it'll actually sit there and do this so that the electron is right next to it. So sodium is like pretending, oh, I'm really sodium plus, I'm an ion, where its electron is literally right next to it. It'll delocalize. So it's not really, it doesn't seem like it's connected to that atom. Okay, now it'll do that. And then the sodium that's next to it will do exactly the same thing. And then the sodium that's right next to it, it's going to do exactly the same thing, right? So then you end up with plus, minus, plus, minus, plus, minus, right? Kind of go on. So it'll make like a sea of electrons so that it'll be able to act like it's alternating between the two. Does that make sense? Yes, no, maybe?
I'm indifferent.
You're indifferent? Okay. Okay, so we have things what we call alloys. Now, the same thing happens with alloys. The only thing is that it'll be between two different atoms, right? So it'll be like sodium and potassium, right? So we can make a sodium-potassium alloy. And so we'll put a potassium here, right? And so because potassium is going to do the same thing as sodium, it's going to get rid of that one and pretend, okay, so it's going to say, hey, electron's right next to me, you know, I'm going to just delocalize it, just kind of push it to the side, and then pretend that now I'm positive, and that's my negative charge. Okay, so it'll actually do the same thing, and this guy is forming an alloy because these guys are interacting as one unit, as a molecule, or not as a molecule, as a compound, right? By pretending the electron is delocalized, right? By pretending the electron isn't part of it. Okay, so then you have a mixture between that sodium metal and that potassium metal. Okay, so let me show you what it looks like, a visual. Okay, so this would be sodium. That would be the electron on sodium. This is sodium. This is the electron on sodium. So it's that electron that it would get rid of to be like a noble gas. So it's pretending like it's a noble gas. And so that leads to a little bit of stability because it delocalized that electron long enough for it to sit there and keep the structure, the metallic structure it exists. Does that make sense? So because we know that sodium, Na, right? Na has one electron that it can use. It wants to be like a noble gas. The only way that it can be like a noble gas is if it gets rid of this. So it pretends to get rid of it. So it doesn't really get rid of it. It just does this. It'll say, I'm in A plus, and then I'm just going to kick that one electron out, right? It's kind of like you have that deadbeat kid, right? And you kick them out to sit there and go get their own job. That's what this sodium is doing to its electron.
Okay.
Okay. So because of that, you get that positive, and then there's the negative next to it. Then it's the positive, and then the negative, and the positive, then the negative. So this guy would be like if we have magnesium, right? Magnesium is 2+. So it's 2+, so representing the 2+ charge. So it gets rid of 2 electrons. One here, and it'll put one here. Then it'll have another magnesium, right? That's next to it. And then you would alternate between your magnesium and your electrons. You have 2 electrons. They wouldn't be right next to each other, but you understand what I'm saying, right?
Mm-hmm.
So now this works in the same context when you're mixing metals together. So we mix metals to sit there and make metals behave the way we want them to behave, right? And we make what we call alloys. Okay, so 18 karat gold. So 24 karat gold is 100% gold. 18 karat gold is 75% gold, 12.5% silver, 12.5% copper. Okay.
That's stronger.
Yeah, it's actually stronger. It is stronger and it's cheaper, right?
Mm-hmm.
Okay, we have brass, right? Brass is going to be, it's anywhere from 60 to 95% copper and from 5 to 40% zinc. So it really just depends on where you buy your brass from, right? And it also will affect the strength of it, okay? We have bronze, 90% copper, 10% tin. We have carbon steel, 90% iron or carbonated steel. And then we actually put carbon in there to kind of strengthen, make it stronger. Pewter, 91% tin, 7.5% antimony, 1.5% copper. Stainless steel, so that's 70% iron, anywhere from 18 to 20% chromium, 8 to 12% nickel, and then you end up with some small elements like magnesium or manganese in it. Okay. Sterling silver, 92.5% silver, 7.5% copper. Okay, so they're going to use the same technique when they sit there and delocalize their ions to sit there and form that alloy. Does that make sense?
Yeah.
Okay, well, that's all I got for you.
That's it?
That's it. Are you sad?
One of these guys.
So for this one, we're aiming for increasing polarity. So let's just start with, all right, I guess the one that you answered. So we have carbon bonded to selenium. So when we were looking at this, we want to compare the electronegativities between the two elements. So what is carbon's electronegativity?
2.5.
Okay. And what is selenium's?
2.4.
2.4. So we're going to find the difference between those. So we'll subtract them. So we get a polarity of 0.1. Okay, then we can compare carbon and phosphorus, which is the next one. So carbon, phosphorus. Carbon's is 2.5. What is phosphorus's?
2.1.
2.1. Find the difference. We get 0.4. And we keep going with that. So carbon bonded to arsenic. Carbon is 2.5. Arsenic is 2.0.
Subtract it.
0.5. Then we get carbon and sulfur. So we get carbon is 2.5. Hi, Dr. Henry. And sulfur is also 2.5. So the difference here is going to be 0.0. So we're just going to arrange these from starting with the lowest to the greatest. So it seems that you put carbon and sulfur at the end instead of the beginning.
That's what when I saw them, I was trying to kind of figure like how they. Yeah, I definitely wasn't subtracting them. So you just pretty much. You could just go to each one and subtract them, and then so it goes from would it be smallest to biggest, right? Or
yeah, if you're working in increasing polarity, you're going to start with the smallest and work up to the biggest. Sometimes they'll ask for decreasing, so you're going to start with the biggest, then work your way down.
Okay, yeah, okay, I see that. It's not too bad. All right, thank you.
Yeah.